Okay, what I want to do today, get everybody's attention, please. So we'll take, Monday, I'll give you folks another day to wrap up tests if you want to, okay, next week. That way you can kind of review things over the weekend if you want to a little bit, before you come back. Today, I wanna push through a few things, kind of an introductory stuff for Unit 2. That way, if people are done with stuff, you can spend the time Monday working on homework if you want, instead of retaking tests, if you're done with everything. Some people are. Okay, so let's remind ourselves here today that we're gonna talk about functions, right? We start with relations though. A relation in math is, what is a relation in math? So, okay, it can be a set of ordered pairs. A relation is what it sounds like. It's a way that you can relate some inputs and some outputs. That's it, right? And it doesn't have to be mathematical. It could be, there could be applications of this that don't even look very much like math. But if there's a relationship between some kind of an input value and some kind of an output value, then that's a relation, okay? So it could be, there's a bunch of different ways that we can express these things. We could do this in the form of a table, for example, and we'll look at examples of these. It could be a table, it could be a mapping, it could be a graph, or it could just be an equation. So what do we call, when we're talking about a relationship like this, where we've got some input values and some output values? Typically the x values are what we call, those are the input values, aren't they?
Yeah.
Right? So the inputs go with the x values. Oops. Okay. What do we call the set of input values? X values. For a relation. It's the set of all the possible input values for a relation. What do you call that? I know you've talked about it, but it's been a while.
It's been some like 7
It's been a hot minute.
It's been a skinny minute for me.
So what about, what do you call that? So the set of all the x values, the inputs, starts with a D.
Denominator.
No.
Division.
What was it?
Domain.
The domain. There you go.
Yay! Smart.
Okay, so the set of x values, the set of all the values that we can input into a relation is called the domain. Now the relation might be a function, but it might not be a function, right? So does that make sense? X goes with domain, but it doesn't have to be x though, right? We don't always have to, like in physics a lot of times we wouldn't have input x's, we'd input usually t's, right? Usually almost everything we do in physics, the independent variable, the inputs are going to be, everything's going to be changing with time. And you want to know for a certain time, what's the velocity going to be, for example, right? Or what's the force acting on an object as a function of time. So a lot of times in the real world, we don't use x's anymore, but as long as it's the input value, could be x, could be t, could be something else, the set of all those values is called the domain. So in math, when we say x values, take that with a grain of salt. It could be other inputs too. Usually it's x, but it doesn't have to be. Okay, what about the set of y values, where those are the outputs? There you go, good. So it doesn't have to be y. It doesn't have to be y. It could be other stuff too, right? But whatever the output is, that's what we call the range. Okay, so then a relation that has just distinct points where they're not connected. You know what that word is called?
No.
We call that discrete.
We'd be discreet
What?
about it.
A discrete relation or a discrete function is one where the values they jump from one to another. They don't. They do it discretely. They're not necessarily connected. Okay, not necessarily connected. A relation where all the values are smoothly connected, and so if we graphed it, it would look like connected lines or curves. That's called continuous.
Why is it called creep? Why can't I make it easy?
So a relation in which each element of the domain is paired with exactly one element of the range is called what?
Wait.
So when there's, for each, in other words, for each input, there's only one output. What do we call that kind of a relation? A function. That's the definition of a function. There we go. So mathematically, each element of the domain is paired with exactly one element of the range. That's what it means to be a function. For every input, there's exactly one output. Okay?
Oh, there's too many elements in this thing. I thought it was a chemistry.
So let's look at some examples of some functions then. So we could do something like, let's just make a set. Let's make a set of values of ordered pairs. Like I could do something like the ordered pair 0, 1. Now what's that tell me if I have an ordered pair? What's the x value?
I don't know.
Dude, I love drawing. Okay,
Dude, Mrs. Roberts used to
Wait,
be
what
so
do you
good
mean?
drawing those little squiggly things.
Yeah,
I was always jealous.
I'm not very talented at those.
Me either.
So what does this mean? Like for this ordered pair here, which is the x value and which is the y value?
X is 0.
X is 0 and y is 1. So we're inputting a value of 0 and the relation is outputting a value of 1. Okay? So that's one ordered pair. We call that an ordered pair, right? And it's ordered because it has to be in order so we know which one's the domain and which is the element of the range, which is the input and which is the output. So what about this? Is that a function?
Is that a 6? Is that another?
That's a 6, yeah.
Okay.
Is that a function?
Yeah.
It is, right? Because each element of the domain, each input, and I've got 3 separate inputs, each of those inputs only has exactly one output, right? So what's
What
an
do you
example of like a non-function? Well, we could do something like,
You want one?
8.
0, 1, 0, 2. And then like, we could do something else if we wanted, 1, 3. What's the problem there? I have a single input, 0, right? The input value 0 has multiple outputs. It outputs to 1 and to 2,
That makes
right?
sense.
And so that's not a function.
So none of them can share numbers.
So the x value cannot map to more than one y value.
Can the Y
So they
value map
can't,
more than
can
one
you
X
make it
value?
simple
It can't.
and just confirm that they don't share numbers?
Can you write a book for dummies?
Wait,
So another
so there
example,
could be more than one
We
Y
need to
value?
Yes,
Like,
yeah,
So there could
there
be
can.
multiple ones for the Y value.
So we could do this, right, like we could do, let's make an example. So like 0, 1, comma, 1, 1, comma, 2, comma, something else, we'll make it something else. So there's an example of, that's also a function, right? Does it matter that there are 2 y values? That's okay, as long as each input value only maps to one output value, it's still a function.
So X's can't be the same, but the Y's
The
can.
y's could be the same, sure,
Okay.
as long as they're mapped to separate x's. Exactly, there's the key,
Yeah,
there's
so
the
you
key.
can have like, you can have.
Okay, and so let's look at the consequence of that. I'm gonna skip ahead a little bit. Let me skip up to here for a second. So is this a function or not?
Yes.
That is a function, isn't it? So what's the domain?
Wait, what?
Eight,
It is?
seven,
Yes,
seven.
it is.
Okay, 8, but now when we write a set like that, when we write a set,
Comma.
we want to put it in numerical order.
So
Right?
7, 6, 8.
It'll be that, right? Okay. What's the range?
3.
3. Okay. Is it a function? Yeah, it is, right? It is a function because it assigns a single element of the range to each element in the domain. So it does work, doesn't it? There are no x values are repeated. Okay, so that one works. So what about this?
Yes.
We're good, right?
Yeah.
It works. There's no x values repeated, so we know we're okay. Okay, there's the domain, there's the range.
Can we also write the range as like the range, you know?
What?
Like 8? The range is 8.
What do you mean?
Or would we have to write each individually?
You have to write them all, because it's a set. if we're using set notation like this, you'd have to write them all. Because the domain is the set of all the input values, the range is the set of all the y values.
So
the
if
output
like,
values.
so like if it's 2, 2, 4, 6, like we have to write both 2s, not just
No, you wouldn't. I understand your question. No, you wouldn't. If there are repeated values, you only write them once. Yeah, you only write them once. And let's look at an example of that too.
I know. I'm just saying, like, yeah, I'm not even,
Well, like we did in the last one. Like, look at the range. The range is just 3.
Oh.
We don't write 3, 3, 3. We just write 3.
Well,
Okay, so we said that is a function, correct?
Yes.
Now, look what happens. The y values are all repeated, but the x values aren't. So if I graph those, look what happens. How do they line up? Horizontally. Yeah, they line up horizontally, okay? Now, what about that? Is that a function? That's not, right? Clearly, that's not. The input value 7 is mapped to 3 different output values, so it violates our rule for a function. It's not a function, is it?
okay, so
Now, look what happens if I graph it. How do they line up? Okay, so is that an accident? No, that's not an accident, is it? That's a way that we can test, because we know that any time that points line up vertically, doesn't that have to mean that we've got the same x value but different y values, right? So there's, what are you gonna say?
Isn't this where you do like the vertical line test?
That's the vertical line test, there you go, right? It's the vertical line test, so.
I don't know.
So the vertical line test just says, here it is, vertical line test just says, if we drag a vertical line across a function, if it only ever intersects the function in one place at a time, then it's a function, then the relation is a function, right? So that one passes the vertical line test, doesn't it?
okay.
This guy, unfortunately, though, does not. Look, there are places on this graph where it intersects the vertical line in multiple places, right? So because it does that, it fails the vertical line test, not a function. Okay? And here's an example of a discrete graph. So this is what it would look like if we just graphed a bunch of ordered pairs, right? What are the coordinates of this point right here? 3, 2. Okay, so that corresponds to the point, the ordered pair, 3, 2, right? And so we've really just got a combination of like 10 or so ordered pairs. When we looked at those sets earlier, if we had graphed those sets I was writing down, it would have looked something like this. But the same rule applies, right? We can look at this thing graphically, and you tell me, does it pass the vertical line test?
No.
It looks pretty good, pretty good, pretty good, pretty good. Oh, there's a problem right there, right? So it fails. Two of the points lined up, so it's not a function. Okay? All right. So functions are, they pass the vertical line test, so an example of a function would be something like this. Right? That's a function. What's a non-function? Well,
The sideways
maybe a sideways parabola, right? Something like that.
Sideways. Sideways parabola. Well, I just don't know.
Okay, so find the domain and the range. I mean, this is pretty straightforward stuff. What's going to be what's the domain of this one?
-1, 0, 4,
6. What's the range?
-9, -5, -2.
There you go, right? Okay. So is it a function?
Yes.
Yes, it is. Okay. How about, we don't have to do all these. How about this one right here?
Wait, 4?
Yeah, it's a function.
That's a function, isn't it? Okay.
Which page is this
The
How
first.
about this guy up here?
Oh.
No.
What's the domain?
No.
Because
5 repeats.
So I got what? -3, 5, 8, and the range?
2,
2,
4, or -6, 0, 2, 4.
Is it a function?
No.
No, it's not. Right there, look. Got repeated values. No. Okay, we can look at these in terms of mappings also. Does this make sense? What's this
Yes.
telling us?
That's a no.
It's a no, isn't it? And why is it a no?
Because it has those.
Okay, good, because the input value 5 maps to the output value 7 and 9. Okay, so that's a no, right? What's the domain? Well, the domain is just right there, isn't it? It gives us the domain very nicely. Yes, ma'am?
If we know it's not a function, do we have to write the domain and the range?
Still do. Yeah, still do.
I can't write this little squiggly name.
I just draw like a backwards three.
Just call Mrs. Roberts.
Make her write it for you.
Oh, I have her number.
What do you mean?
She
So
told me
that's a
very
no.
racist woman.
I
And-
told Jones the other day that I don't.
You guys probably have to write down the domain and the range every time. You get that.
This
Is this a function?
Yeah, this is Jones said hi to
Yes.
Which one?
Yes.
Everybody up here, let's take a vote.
Yeah.
What do we think?
Yeah.
Yes.
Yes.
Yeah.
It is, isn't it? And is it a problem that both of these are mapping to the 7? No. Okay. There's only one arrow leaving each element in the domain, right? Each x value, so we guarantee we're okay. That's really what kills us here, is that I have 2 arrows leaving 1 value.
See, okay, that makes so much more sense.
Okay?
No.
The people
Function or not?
my friends were.
No.
Okay, so let's do one of these discrete ones. What's the domain here?
1, 2, 3, -3, 0, and 2.
Good job. And you get those because those are just the x coordinates of the points,
Wait,
right?
there's an extra one. There's one hiding at the bottom.
Oh, there is.
And there's one of what?
I'm writing in pen.
Maybe you don't write.
So what is that, 4?
Yeah.
No, 5.
So what's the range?
It's
Wait.
I bet it's a 5.
Okay.
Negative.
No, it's going on the x value, not the y.
Oh,
Yeah,
okay.
-5, -2, -1.
Oh, yeah, negative 5.
But tis is not a function.
1 and then 4?
You're sort of screwing with it, sorry.
Do I agree?
Horizontal.
I'm kind of slow.
Vertical.
Okay.
No. What's
Okay.
the slanted one?
It's not
Okay,
a
questions?
function.
Slanted.
No function.
All right, hey, so we're getting, this great class, but we're getting a little sidetracked here. I want to get through this so you guys can work on it. A little bit more sticking to business. So what about this one? We got a
Yes.
line. This is different. These are not discrete points anymore.
Vertical
What are all the x values that exist that are input values for that line?
Where it crosses like a solid point.
All of the numbers.
Well, no, it's like where it hits a solid line.
Yeah. Booyah!
Right?
You smart.
Okay, because the line goes forever to the left and the right, correct?
I don't
So
know.
there's no x value that I couldn't input and get back a y value. Agreed?
Yeah.
So what would it put?
So, what'd you prefer?
So what's the range?
All.
Because it goes forever. And it's sloping upwards, right? If an ant walks far enough along this to the right, he's gonna go, there's no limit to how high he could go, right? If an ant walks to the
That's
left,
not first.
there's no limit to how low he could go, right? He goes forever.
I don't know.
Is it a function?
Yeah. Yes.
What are those?
Okay, we did this stuff.
What's wrong with them?
Okay, what's the,
Oh,
all right, so let's,
No and no.
what are we thinking about? So it's not a function, you're right.
Why? Can you explain that? Because not all of us are.
Okay, why is it not a function?
Vertical line test.
Vertical line test, look
Oh,
right
right.
there.
Okay, move on.
There are points that line up vertically. Okay, but what about the domain?
I don't. Well, it's not working.
Okay, well, so raise your hands, raise your hands.
X is greater than or equal to -4.
That's correct. X is greater than or equal to -4, because would you agree that the leftmost point is negative, has an x value of -4? That's the furthest, if an ant's walking along this relation, along this graph, the furthest left the ant could ever get is -4, right? Now, he can go to the right forever, but he's limited to how far to the left he can go.
Because they would look for the R.
So R would. Wait.
Okay, now we got people, hang on, I have a question here.
So would we put it in the little bracket thing, the X?
If we wrote this in interval notation then, you guys tell me what would that look like with interval notation?
-4.
Okay, now hold on. Oh, yeah, you're right.
Yeah, the
Negative, right. -4, comma, infinity, with a bracket parentheses.
Well, I'm talking about
over right.
that even like wiggly thing.
Oh, no, okay, okay, good question. Now, why,
What are the squigglies called?
Yes.
So we can talk
They're-
about them without referring
they're
to
called,
them.
they're script brackets, yeah.
Okay.
Okay, why is it that the script brackets don't make sense here.
Because they're not a set.
Well, it is a set. It's a
not
set,
proper
but there are different kinds of sets. If we go back and look at these previous sets we had going here, like these guys. Okay, they make sense here because this is a set of discrete values, a finite set, right? The number of x values, how many x values are there in that set? 3, exactly 3. How many x values are there in the domain of this set? Well, in fact, they're an infinite, right? Now, what is it? If you think about a line, you probably never talked about it this way, but probably the best definition of a line is that it's a locus of points that adhere to an equation, right? But the key word there is it's a locus, meaning it's a fancy math word for set. A line is just an infinite set of points. Think about like, if this is a line, let's take this ray, for example. This ray goes on forever. Think of it like if you were to string a bunch of beads together on a necklace. If you made the beads really, really small, that necklace would start to look like, it wouldn't look like beads, it'd start to look like a string, wouldn't it? Well, what if the beads were point-like, infinitely small? That's really what a line is in a sense, right? It's an infinite string of infinitely small beads. How many are there? An infinite number. You could never point to one because they have no size, right? But there are an infinite number of points that comprise this ray and that ray. And so the number of the set of x values that we could input are infinite. In fact, they start at -4, but even after you've gone to the right only by 1, how many points are between x equals -4 and x equals -3 on that graph? An infinite number, right? So we need a different kind of notation, don't we? We can't use the set script brackets anymore because it takes us a long time to write down the coordinates of all the infinite x values, right? So instead, we just say this. X is greater than or equal to -4, which implies all of the infinite values that are greater than or equal to -4. Okay? What's the range?
All real numbers.
All reals, right? Because this line slopes down forever and that ray slopes up forever. Okay? Make sense?
Not
Okay.
really.
Well, ask a question.
Let me figure out my question really quickly. Just give me a second.
There's another way to think about this.
Wait, okay, I got it. So,
I counted the same 3 times.
So, if you have,
How many numbers?
so if
3 to
negative,
each time.
so is the output that way because the line stops at -4 and it only goes past there, but when it's horizontal, it goes both ways?
Well, it's never horizontal. There are 2 parts to this relation, right?
No,
There's
but
2 discrete parts. Here's a way to think about it. Here's a way to think about it that might help. And this will help in the future too. When you're thinking about things like you want to find domains and ranges. A way that you could talk about this using math terminology that you'll get to later in life is you could think about them as being projections. They're projections of the x and y coordinates onto the x and y axes. So imagine, this will help. Like later when you get into some physics and things, this is helpful. When you think about vectors, about components of vectors. So what if you were to squeeze this function horizontally, everything moved, I could take each of these points and I'm going to squeeze them horizontally onto the y-axis, right? What kind of a mark would it make on the y-axis if I did that? It would be the entire axis, wouldn't it? Or another way to think about it would be, what if you were shining a light horizontally and you were casting shadows onto the y-axis from the function? This function would leave an infinite shadow, right? If I'm shining it from both this direction and this direction, these places would leave shadows on the y-axis that would go the entire y-axis. But what about the x-axis? What if I were to squeeze this thing vertically up onto the x-axis or cast shadows onto the x-axis? Do you see that in that case we get something different, right? The shadows that it would cast would start right there and move to the right, but there would be an edge to that shadow, wouldn't there? Right? So that's one way to think about the domain and the range. If I squeeze or cast shadows, where do they end up?
Okay,
If I push them up onto the x or y axis.
But I just need a simple. So is the output that way because no matter what you do, the x value is always greater than 4, but the r is because they go forever, both
Well,
ways.
because the range is a
Yes?
set of y
Okay.
values.
Got it,
right?
got it.
Okay.
Cool.
Yeah, 'cause it
Don't
goes
keep
forever.
talking, you're just gonna confuse me.
Okay, so what about this one over here then? We've got this ellipse, function or non-function?
None.
Non-function.
Thousand past the line.
Okay, so what's the domain this time?
Oh, it is
No?
greater than or equal to negative 2 and less than
Well,
or
do we
equal
write
to
that in the
5.
set?
Okay, say that again, Jim.
It is greater than or equal to negative 2 and less than or equal to 5.
Good. Okay, now you can't write it as a set because there's an infinite number of points, it's continuous. We have to write it using either inequalities or interval notation, right? So written with an inequality, that's correct, isn't it? Now, why do we include the endpoints there? Because there are places where when the ant is walking around this ellipse, there are places where the ant actually has an x-coordinate of negative 2. There's one place, one point. And there's one point right there where the x has an x-coordinate of 5. Right?
So
And then he's going to walk all the x values in between. If I squeeze this thing onto the x-axis, those are the x values that we'd have on the x-axis if I squeeze the whole thing onto the x-axis, right? Yes, ma'am.
So then for the range, would we just do the same thing?
Yep.
Like.
So you tell me, Maria, what's the range? Y is what?
I can't tell the bottom number. Like negative 2?
Okay, is greater than
I
or
think
equal
it's-
to, right?
Yeah. And
1.5.
then,
And less than or equal to
about 4 or 5?
4? Okay, make sense?
Oh, okay.
Wait, I think it hits in the middle though.
Okay.
It definitely does not.
No, it hits right there. The coordinates of that point right there.
Yeah, but that's halfway between 1 and 2.
Okay, but we're talking about the range. We don't care about the x values there, right? All we're concerned about are the y values. If I squeeze this
Oh,
thing,
got it. Okay, I'm
Horizontal.
stupid.
Not,
'cause
not this way. up and
My
down.
brain needs to be quiet sometimes.
okay, so how about
I don't
this?
know either, okay?
So these functions right here, or these relations, we had to determine if they're functions. How do we find the domain and the range? Well, as we move through the class, we'll practice finding domains and ranges in ways that just rely on algebra. Okay, but we're not quite there yet. I mean, as we get to talk about quadratic functions and what their graphs look like, we could easily answer what the domain and the range are based on the parabola that we know this is going to develop. But we haven't reviewed that stuff. You might still be able to do it, but we're going to use technology for now. So all you have to do on this is we're going to use the Desmos graphing calculator.
Wait,
So the Desmos graphing calculator, let me introduce you to that, and it's embedded in the assignment. So it's literally like each question that needs the Desmos calculator, it's got one sitting right next to it. Quick question, yeah.
I forgot.
Okay.
Move on.
So
We're good.
so we can type this using y's is fine. So we'll say y equals negative x squared plus 3, okay? And there's our function when we graph that. Well, in Desmos, it does some really cool things.
So
Desmos, if I click on the function, let me zoom in a little bit too. If I hit the home button, it takes me right to the, zooms in on the origin. So when you click on a function, it gives you little gray suggested points at the intercepts and at the maxima and minima. So that's an important point right there. What's unique about that point?
That's,
It's the only one on an axis.
Well, okay, true, but there's something else.
it's the top point of the range.
Okay, it's the maximum of the function, we say. It's the biggest y value of the function, the highest value of the function, okay? So given that graph then, can you tell me what the domain and the range are? Somebody who hasn't had a chance to answer yet, help me out here and tell me what the,
What was the point? We don't see.
0. Okay.
so, and there's the point, yeah, and let me take a picture of that, just put it on so we have it.
So, wait, so would the
So there's the picture that goes with number 11, right?
So would the output be x is less than or equal to 3?
Almost, but it's not x.
Or Y.
Yeah. So y has got to be less than or equal to 3 is going to be the range. Now, what's the domain going to be?
It's gonna be all real numbers.
All real. Yeah, because now we can't see the entire graph, but the implication here is this parabola, it's never vertical, right? It's always inching to the left and the right. As the ant moves to the right along this parabola, he's moving down pretty steeply, but he's always moving to the right also, isn't he? As he moves down in this direction, he's moving down, but to the left all the time. And so the domain is all reals, right? If we go far enough, there's no x value we couldn't get to on this function, okay? Is it a function?
Yes.
Yes, it is.
Who said no?
I-
Line test.
The vertical line test, yeah. Some of them are, some of them aren't. So what about this one? What's that equation gonna be? If you think about what would I get if I graph it? I don't need anything specific, but what's the shape gonna be of that?
It's gonna be a line.
How do you know?
Okay, how do you know? Well, we haven't even talked about it yet, but I just was asked. So it matches the form y equals mx plus b, doesn't it?
Yeah, so but how does that give you what it looks like? on the-
Okay, so it doesn't, I don't care exactly what it looks like, but what is that the equation of?
Oh, slope.
Okay, it's the equation of
this.
line, right?
Oh,
It's
so that's how you found out it.
Wait, but how do you know what?
And don't panic if that didn't immediately jump out at you. I mean, we're gonna review this stuff.
Oh, so it's because like we put, so the x is squared, so like m would be our number, so it's like
M
how
is-
would we know it'd be the line?
So M stands for slope, right?
Yeah.
And what does B stand for?
The
How much
y-
is starting point, the
The y-intercept, okay, and we can graph the thing, I mean, that's fine. You guys are gonna have access to the graphing utility for now to do all this stuff. But I just wanna point out that we don't even probably need to on this one. If it's a line that has a slope of -5, is it horizontal or vertical?
Neither.
it-
So
No, I mean, it's sloping, it's slanting somewhere, isn't it? If it's got a slope that's -5, right? So we could kind of finesse our way through this without even having to graph it. If we know it's a line that is slanted and the line goes forever, what's that tell you about the domain and the range?
they're all real numbers.
They'd have to be all real numbers, wouldn't they? Right? And here, let's look at a graph of it and see.
So would the maximum be 5?
Because it's a line, right? That's why
Right,
it's all reals?
right.
Okay.
So would the maximum be 5?
So if we graph this guy, whoops, I don't want to do that. If I graph this guy, okay, so now I'm just going to change this to y equals -5x
Well,
minus 1. And look what we get when we do that. You see my point?
Yeah.
So there's no maximum either way, so RR?
It's got to be all reals, doesn't it?
Oh,
So-
I totally get, okay. That makes sense, so like it'd be 5/1 if we put it in the fraction, like, because if you put it in the fraction form, that would be when you're younger.
Right.
Okay.
So we know that because this has a slope that's not equal to 0, right? So it's not a horizontal line.
Yeah.
We know that the ant that walks along this line is going to move to the left forever and the right forever and up forever and down forever if he goes far enough, right? So we know right away that this has to be all reals for both.
Oh, so it's
Is it a function?
So if you
Yeah.
know it's
Yes.
a line, you know it's real, and yes, right?
Well,
Pretty much.
not necessarily. Let's take this line right here. What about the line x equals -1? Okay, that's a vertical line, right? So if it's a vertical line, does it pass the vertical line test?
No. It
Can you explain
definitely
how
does this. So if you know it's a slanted line,
A slope.
Right. If it's a line
slope.
with a slope that's not equal to 0, right, a non-zero slope, then that's a slanted line, and then it would have to be all reals. Now this
Okay.
guy, if I graph this one though, this function right, or this relation right here, it looks like that, doesn't it?
Oh,
Right.
okay.
And so obviously that's gonna fail the vertical line test pretty miserably, because when I drag a vertical line across that, there are an infinite number of points that line up vertically.
So for that one, the input would be -1 and the output would be like all reals, right?
Right. So the domain is just -1. That's it. Or you wouldn't have to write it that way. You could just write x equals -1 is the domain. There's only one value. What's the range? All reals. Okay. Now what about this guy? What kind of line is that?
Yeah.
That's horizontal. So is that a function?
Yes.
Yeah, that is. What's the domain for this one? All reals. What's the range?
-7.
Okay.
Okay. Oops,
You
yeah,
did
you're
really
right.
like one too. And then I did that.
Yes. There we go. Okay?
I don't know whether I'm tired or my brain's just saying, athletic.
Okay, so then the other thing we can do with functions here is, now functions are a big deal. We use functions a ton in math because they represent, they're mathematical relationships that can be important to us. So if we define functions and we use them as models, like for example, we might have a function, let's say we have a polynomial function that is describing the economic output of some company or something, where the input value is going to be the month of the year and the output value is going to be what the economic output of that company is, right? So in that case, we could base these on data, and we're going to actually do a little bit of that like next week. We'll take some data and we're going to use the raw data to develop we're just limit ourselves to just linear functions for now, but later on in the class we'll do this for higher level functions. We're going to come up with a best fit line using technology. We're going to use the data and we'll come up with a line of regression. And we can use that line of regression to make predictions. It has predictive value, right? So like let's say we took data in here and we said, okay, we're going to estimate, so based on your height, what's your shoe size or something like that, right? And for everybody in the room, if we did that, we'd gather a bunch of data, and we could come up with a best fit line that predicted what your shoe size is going to be based on your height. So would that apply to people that didn't have exactly the same heights as people in the room? Of course it would, right? You see where I'm going with this?
Howard thought.
So this is what we call a mathematical model. Mathematical model is a pretty powerful tool. Like we could use this, even though there's nobody in here that is 4 feet tall, we could use this model to make a prediction and say, okay, nobody's that tall in here, but if they were, what would their shoe size be based on our model? Is it guaranteed to be right? No. Is it guaranteed to be, well, it's not guaranteed
It's a
anything,
good range.
but it's more likely to be right than any other random value you would take. Does that make sense?
So it'd be like a hypothesis.
Okay. It's kind of. I mean, it's not really kind of, yeah.
So you're basically taking a bunch of discrete values and making it into a,
That's what we're going to
function.
do when we build a mathematical model.
so you're taking a bunch of points and kind of evening it out.
And we're using a statistical tool, which, we're not going to go into it's a least squares regression process. And at the end of the year, if we have time, we'll kind of talk about how you can do that, how you can build up a regression, how you build up the whole process of linear regression or quadratic regression or anything. But for now, it's just our way of coming up mathematically with the best fit line. This is a lot of what people do with math. I can tell you, when I graduated from college, there were a bunch of economics employers that they wanted quantitative economists. They called quants. They wanted these quantitative economists, and if you had graduated from at my college, if you graduated with a degree in physics or mathematics, they were ready to hire you without even an interview process, and for an economics job. Didn't matter if you'd ever taken an econ class in your life. They figured if you're smart enough to do math, that kind of applied math, you can go and learn economics, go read a book, and you're fine. But it takes years and years and years to develop the tools to be able to do the math. And what did they want with this math? Why did they want these people that could do mathematics? And they're paying them just ridiculous amounts of money. Because they want to build mathematical models that are going to predict how they should invest. Right? If you're investing in these big investment firms on the East Coast, where they're annually investing, tens of billions of dollars, all these people are how do they make their money? They make their money based on how profitable those investments are. They take a small percentage of the profits made from those investments, right? And so if they can find little mathematical models that can increase their productivity by 1,000th of a percent, right? 1,000th of a percent of $100 million is an awful lot of money, right? You see what I'm saying? So you start to accumulate these very large savings if you can if you can increase the profitability on these thousands of daily these transactions that occur where all this money is moved, right? And so, but how do they do that stuff? Well, it's all built on this idea, okay, we're gonna look at this data. Can you build us the most accurate possible mathematical model that's gonna be the best predictor of what we should do when we're investing this stuff in the future, right? So even though we're starting just at kind of at square one with this, there really is, this is what you do and this is how you apply it in math in real life. Whether it's in science or economics, you build mathematical models and the whole goal is just to become good enough at math that you can do that well. In a lot of jobs, that's what you do, okay? We're out of here in 1 minute, aren't we?
Yeah.
Okay.
You know, if I went to Stanford, I'd probably say Stanford instead